Welcome everyone. So this is our 75th live stream geometry. We have 2 people here so far and more might join later. And today I'm taking problems from just various users I found on the Art of Problem Solving forum. So last week I took problems from the professor Jean-Louis Aimé, but I found out that he took a lot of his problems from random pages on the Art of Problem Solving forum. So I kind of investigated those and the different users that he took the problems from, and I just picked some problems from them. So that's what we're going to do today. So if you want to join us in future sessions, feel free to email me at mgreenb801@gmail.com. The sessions are every Sunday at 8 a.m. US Central Time. So my email, mgreenb801@AOL.com, mgreenb801@gmail.com. Did I say AOL? It's in the description of my video. All right, so I'm going to share my screen. All right. So here's the first problem. Let me maximize it. It looks simple, but I'm not sure how simple it really is. So we have a right triangle ABC. So I'm going to draw a right triangle. I guess there's a couple of different ways to draw right triangles, but I usually just do it like this. Oh, whoops, I gotta use this. And then we draw the incircle. So I'm gonna hide this and let's draw the incircle. And then we draw the 2 angle bisectors, BD and CE. And then we draw the midpoint of DE. So D is on CA and E is on AB. Let me move this out of the way. So this is D, this is E. Whoops, not that point. I might have to zoom in a little bit. Let me fix this. So E should be this point. There we go. And then we draw the midpoint of DE, and that's M. And we want to show MI is perpendicular to BC. So yeah, it might be a really easy, it looks kind of easy, but I'm not sure if it really is or not. It's hard to tell. So let's try to solve it. Let me make this smaller. There we go. I think that looks good. Whoops. Call this point F. So we want to show MI and F are collinear, basically. We know MA equals ME equals MB because this is a right angle right here. If DE intersects BC at X, then we want IX to be parallel to DE. All right, so I'm going to draw that. Oh, this is a tricky diagram. Let's see. How should I draw this? Maybe something like that. So we let DE intersect BC at X, and then you're saying we want to show IX. Well, that doesn't make sense. IX can't be parallel to DE. Oh, it's all right. Let me go back. Yeah, that point still might be useful later. We'll see. But yeah, maybe we can somehow use projective geometry. So basically, we want to say that we want to show that M projects to F. So I think, yeah, you're trying to use projective geometry, right? It's actually, it's the same as showing that cross ratio is 1, right? I think that's what you were trying to do. Basically, well, you're saying if we draw the parallel through I to DE and we let it intersect BC, then you want to show that cross ratio is 1. So here's another way to think about it. Basically, yeah, we can draw this line because we know that this cross ratio is 1, right? So basically, yeah, so we want to draw this, and then we want to show that line, let's see, we want to show that this is parallel to DE. So we want to show IJ is parallel to DE. All right. It's a good diagram. Let's draw IJ. And it looks like Rodrigo's joining us. Oh, 2 other people, yeah, are also trying to join. Hey, Rodrigo, it's been a while. Thanks for joining. And it looks like we have someone else too. Thank you both for joining. So we're on the first problem, and it looks kind of it looks like it should be easy, but I don't see a solution right away.
Hi, Michael. Nice to see you. It's a long time.
Oh, yeah. Yeah, thanks for joining. Okay. So, yeah, I wonder how helpful this is, like trying to show IJ is parallel to DE. Yeah, so for the 2 of you that just joined, it's a simple problem. You just have a right triangle, and D and E are the feet of the angle bisectors from B and C, and M is the midpoint of DE, and we want to show MI is perpendicular to BC. So yeah, we have to use that as a right triangle somewhere. Yeah, what do we know about IJ? Is IJ like perpendicular to AF? I think it is, right? I think that's like a well-known fact. Yeah, because this is the polar of J, because since J lies on the polar of A lies on the polar of J. So by symmetry, this is the polar of J. And so that means that IJ has to be perpendicular to AF. So then we want to show that DE is perpendicular to AF. Is that obvious? Is that just an angle chase? I think it is. Yeah, that must be it. So yeah, I think that solves it because we can just angle chase all the rest, right? And that should do it. Let me label this point. Just thinking about how to do the angle chase. So we want to show that this is a right angle. So angle AED, we want to show angle AED plus angle EAF is 90, which is kind of the same as saying angle EAF is equal to angle ADE, and that's obvious. Okay, so yeah, that should solve it. And yeah, that's where we use that as the right triangle. Okay, it's an interesting solution. So I'm going to write it up. All right. Let me shrink this diagram a little bit so that I have room to write the solution up. Okay, so let the incircle be tangent to BC, CA, and AB at F, D, and E, respectively. Oh no, F, G, and H, sorry. And then let GH intersect BC at J. Then basically, since AF, BG, and CH concur, then that means that B, C, F, and J are in harmonic conjugation. So you have AF, EG, and CH concur. So this is something I've used many times on my channel. So we have B, C, F, and J are in harmonic conjugation. And I don't even know if we need that, actually. Well, yeah, we do need that, yeah. So since J lies on the polar of A lies on the polar of J. So basically AF is the polar of J. So then that means that IJ is perpendicular to AF. So might as well put this all in one. So we have IJ is perpendicular to AF. And that means that then I'm going to also show that ED is perpendicular to AF. That is true just by an angle chase. So basically angle EAF is equal to, yeah, so I want to show these are perpendicular, but wait, I think I might have thought it was more obvious than it really was. There might be a little angle chase that I need to do. So angle AED is angle AEC minus angle DEC. Yeah, is there a fast way to show this, or do I have to do some calculation? Let's think about this. Oh, whoops, sorry. I might need to do a little calculation here. So angle BAF, that is 180 minus angle B minus angle AFB. And angle EAF, I'm sorry, angle AED is 90 minus ADE, which is 90 minus DEC minus DCE. And DCE is half of angle C, and DEC yeah, what's the best way to do this? So we want to find a relationship between angle DEC and angle AFB. I think we just want to show those add up to 90. I'm not sure. Actually, maybe not. Okay, yeah, I think this should be doable, but.
Michael, I think this problem is on Ivan Chen's book.
Evan Chen?
I remember the idea for it that consists of taking the parallel through BC, passing through L.
Okay.
I think this is the way to solve it.
Something like this?
Yes, and then taking the intersection points of this line with AB and AC.
Okay. Let me see if I can make point H be a little farther away. Or I could just get rid of point H, but sorry. Okay, so there we go. So intersect that with AB and AC. I'm going to zoom in just to draw the point, and then I'm going to zoom back out. Oops, it's still hard even. It's the intersection with the circle. There we go. I can zoom back out. Might take a little while. Whoops. All right.
And then the thing you want to show is that, for example, I, M, GL are cyclic.
Okay. I and J, or I and KL, or sorry.
No. I, M, G, and L.
Oh, I, M, G, and L. Okay. It doesn't want to do point N. Hold on one second. Why don't I hide point H for the time being? There we go. All right, so INGL or IMGL. Let's see. So IGL is 90 and okay, yeah, that would solve the problem basically. All right. Let's think about this. Yeah, so if this were cyclic, what would that be equivalent to? That's the same as saying angle MIG is angle C. And yeah, I'm just thinking how we would show that. Let's see. That is tricky. So can we use power of a point? Let's see. We could try to show that, yeah, I'm thinking like AG times AL. But we need two lines. So maybe NM times NL. But what would the other line be? Let's try something. I keep selecting H. Let me hide H. And let me
Okay, I think I remember how to solve it.
Oh, you found it?
Yes.
All right.
You take M to be the intersection of line IF with ED. And you
Okay.
want to prove that AM is the median of BAC.
Okay. Okay. So let me delete point J. And that might make it look a little nicer. I'm gonna unhide
Mhm.
H. Okay. So we redefine M to be the intersection point. So I'm gonna hide ML.
Mhm.
All right.
And the lemma that is well known is that M lies on the median of the triangle ABC.
Okay. I see Sriyansh just joined. Thanks, Sriyansh. Okay, so it's well known that M lies on the median of ABC.
Yes. And the way that you can prove it is by taking these points, L and N,
mhm.
and then, for example, you want to show that MN is equal to ML.
Okay, so basically you draw the parallel through M like before, right?
Mm-hmm.
Sorry. Let me just a second, sorry. So I'm gonna hide H for now, and then I'm gonna unhide it. Okay. All right.
Sorry, who are these points, E and D?
D and E. Oh, Sriyansh is our first
Okay,
problem.
okay. I don't know. I think I've mistaken. Sorry. The thing with the lemma is if you take the points H and G.
Yeah.
And
So we know that
yeah.
these are cyclic then, right? So we know IMGL is cyclic because this is a right angle. And we also know that this is cyclic. So that might help a lot.
Mm-hmm.
I might call this M prime just because we want to prove it's the midpoint of BE. Exterior angle bisector. So yeah, I don't think M is a median of AM prime is the median of ABC, but it is the median of AEB. So, or we want to show that. So yeah, maybe that has something to do with it. Um, but you think the problem starts out this way, or the solution that you read maybe? So let's think about this. Yeah, it seems like showing DE is perpendicular to AF should be doable. I'm just not sure. Yeah, it's tricky. Like, I wonder if we use a lot of signs because we want to show. Do we want to use the angle bisector theorem somehow? Like AD over DC is AB over BC. We want AED. Oh no, I don't think AED is isosceles. Yeah, is there any way to find angle DEC in terms of angle AFB? If we can find angle DEC in terms of angle AFB, that would solve it. Hmm. I would be very surprised, but yeah, let me see if BEDC is cyclic. Yeah. You coordinate bashed it. Oh no. Let's see if we can find a solution without coordinates. Uh, yeah, we just need to find angle DEC. Yeah, we might be missing something. Yeah, I like Rodrigo's idea here. So we have these two cyclic quadrilaterals. So can we use projective geometry somehow? Project, what do we want to project through? Angle EID is 135. And so BEI is similar. Oh. So if that's 135 degrees, then BEI is similar to BAI. Okay. And so that would give us some of the angles we want. Yes, I think that will do it. So basically, yeah, BE times BA is BI squared. But okay, so going back to what I said before, that would give us angle BEI is angle AIB, which we can calculate. And hold on just a moment. So yeah, EIB is 135. So EIB is 45. Okay, yeah. So yeah, it really is just, should just be an angle chase. Because I think so, at least. So BEI is similar to BAI. Yeah, but I want angle DEC. I'm not sure if that gives me what I want. Although it might, yeah, okay, yeah, I think this is just an angle chase after that. Okay, so we have, so this is 45 degrees. This is B over 2. So this is 135 minus B over 2. So yeah, we have this angle, we have this angle. Yeah, I like your observation. BEI is similar to BAI. That has to be helpful somehow. AHIG is a square. We haven't used that yet. Oh, you know what? Okay, I think that, so I think all we really need is that DEI plus EDI is 45 degrees. And then from there we can find, oh wait, I want to find AED plus EAF. Yeah, this is tricky. So I wonder if we can use this. So this, and the tangent at K all concur. Um, yeah, let me actually undo that. So what if I did this? So BEI is similar to BAI. So we know BEI is tangent to AI. Oh, sorry, I don't think I did that right. Oh no, AEI would be tangent to BB. So yeah. Wow, this is tricky. I wonder if we can show that like EA squared minus EF squared is DA squared minus DF squared. How would we calculate those? Yeah, I'm still trying to use that similarity that Khan mentioned. Really? You don't think there's got to be a synthetic solution, right? I can't imagine that you can only do this with coordinates. Okay. Some trig. All right. Let IF intersect ED at Q. Okay, so QE over QD. Okay, I'm just reading through it. IE over ID. Sine EIM over sine DIM. So EIM you're saying is equal to CIF. Okay. Okay. Oh yeah, you just changed Q to M, or M to Q. Okay. Okay. CIF. Okay. All right. So All right, so we can, for that solution, we can delete n and l. Okay. We'll call this Q. All right. All right, so I'm just going to type up that solution for now, and then after the session, let's see if we can find the synthetic solution. But wow, this is tricky. I would have never imagined that a synthetic solution would be this hard. Let's... Let me copy copy this. We put it in LaTeX notation. And let me put a couple spaces in it and see how it looks. All right. Ah, that didn't come out too bad. Let me put a backslash before the sign to make it look nicer. I think if you can do it this way, I bet there's also a way to do it with projective geometry. Oops.
So the main idea is to QA over QD into some common value and angle in triangle ABC and use the condition that ABC is a right angle to solve it.
Oh, sorry, I couldn't hear you that well. Are you muted? Or I think you were unmuted for just a second. Say that one more time. It's all right. So yeah, let me read through this. So QE over QD, it's IE over ID times sine. Oh, let's change the M to a Q. EIQ over DIQ, which is IE over ID times sine CIF over sine DIF. And that is, yeah, FC over IC and yeah, IB over IF. And FC over IC is IB over ID. Let me think about this. Okay, oh, you just rearrange stuff. So the FC FC is still on the top and IB is still on the top, but ID and FB. See, I'm trying to understand this one. So this I get. So IB over ID is, yeah, I think there's a few extra steps. So let's see. So I agree with this step. Yeah, I should send them all out. I think I forgot to send them out, but yeah, I'll send you guys the GeoGebra files. So from here to here, I think everything was rearranged, but so ID, IE, IB, and FC are on top, and ID, IC, and IF. ID, IC, should this be IF right here? Instead of FB, should this be IF? Oh no, I think this should be, let's see, sine BIF. Okay, this should be BF, IB over BF. And then this is just rearranging stuff. And then IE over IC is AE over AC. And then IB over ID is AB over AD. And then this we stay the same. So, okay. Is this last line obvious? Yeah, you just switch the order of everything. So this very last line here, okay. Okay, because, yeah, okay, those are just right triangles with angles B over 2 and C over 2. Yeah, okay. I see it. So, because basically we have ABD is similar to IBF. So I'll say it like this. Since ABD is similar to IBF and ACE is similar to ICF. You can get those last two ratios and that solves it. So, okay, so this means that QE equals QD. And that implies Q equals M. And that implies MI is perpendicular to BC. That's interesting. All right. So yeah, I like the idea. So yeah, I'm going to see after the session if, yeah, there's a more synthetic way to do it. Thanks for the solution. All right. So here's the next problem. So we have a triangle ABC with circumcenter O and orthocenter H. And AH cuts the circle at P. So this is O. And let's draw the perpendicular from A to BC. Oh, the other con. So he told me he might join in a little bit, but he's like been busy with school. So I'm not sure when he's going to be able to, but yeah, hopefully he will come back on soon. So yeah, we'll see. So this is P and this is D. And we also want to draw the orthocenter H. So if we reflect P over D, then we get H. That's a well-known fact. So I'm going to hide that. And D, E, and F are the reflect. Oh, we don't want another D. So I'm going to call this K. So we want to reflect O over each side. I'm going to call it D, E, and F. And then so EF is parallel to BC. You might as well draw OD, OE, OF, right? So yeah, EF is parallel to BC. In fact, yeah, this triangle is similar to the original triangle because all the sides are. In fact, is it congruent to the original triangle? I'm not sure, but okay. So AE and AF intersect BC at N and M. So we're going to need to make this diagram a little smaller. And BC and BD, or BD and CD, intersect the two sides at X and Y. Okay, so one sec. I'm going to look at the chat in just a second, but for now I'm making it a little smaller so that we can see the other points. So oh, they are congruent. Okay. And let's turn these into rays. So AC and AB. Okay, so this is N. This is M. And we need to see X and Y. So I'm going to move this up. And maybe something like this. So now we can see X and Y. So this is Y. And this is X. We want to show P lies on the radical axis of those two circles. So BNY and CMX. Now this triangle ABC almost looks isosceles, so I'm going to try to fix that. I don't want it to look isosceles. So yeah, I don't even know if we really need to draw these circles. We just need to know that P, so that P is the same power with respect to them. Let's see, how do I make this diagram? I don't want, this is an interesting diagram. It's hard to make it look that nice, but I'm going to try my best here. So if I do it a little bit like that, that looks okay, I guess. Let's make sure I can see point X. All right. Let's check the chat. Oh, is it really that he labeled D and E as midpoints of AB? And then we are done by the midpoint theorem, we are done. Wait, so wait, are you saying you solved the problem? Oh, that's a proof of the congruence. Okay, yeah, because each side is the same length. I see. So yeah, it's a weird diagram. We want to show P lies on the radical axis of BNY and CMX. So we want to show it has the same power. Yeah, this one looks hard. I wonder if we could use like Casey's theorem. That might be a little tricky. Yeah, this one looks hard to me. You guys want to see if we can find an easier problem, or do you want to keep trying this for a little bit? All right, I'm gonna move on to another one. See if we can find something easier. This one looks like it might be easier. And I feel like I've seen this kind of configuration a couple times, so that might make it easier. So we have a triangle ABC in center I and circumcenter O. Let's draw the in circle. First, I'm going to call this O. So I've seen a lot of problems where it's like it has the orthocenter of BIC. I feel like that's a kind of common configuration. So whoa, so H is like way up there. Let's see if I can make H closer to the rest of the diagram. Maybe something like this, shrink it a little bit. And okay, so E and F are where the in circle touches AC and AB. Let me draw D first. So basically, we want to draw the intersection of the circle AEIF and AIO. And we want to see where they intersect the circumcircle of ABC. So this is S. S is the Sharkey double point. and T is this other point. And this is S. And we want to show THIS is cyclic. That's very weird. Interesting. So I is the orthocenter of BHC. And I feel like, yeah, let me draw a triangle BHC. And let's draw the circumcircle of BHC. Because so the distance from, so HI should be twice the distance. Yeah, HI and D are collinear. And not only that, I'm going to draw the other intersection point with a circle. So ID is equal to DG. So if T, H, I, and S were collinear, what would happen if we try to use the radical axis theorem? So we would have, okay, we have three circles all passing through A. It's kind of interesting. Point E disappears when I move stuff around. I wonder, maybe I could use power of a point and I could let TS intersect this. And then I could try to use power of a point. Is ST tangent? Let's see. We have this circle and this circle. So we want to show, I wonder if ST is tangent to that circle. I don't think it is. So let me draw the midpoint of BC. So it's just me and Yukon. Let's see if anyone else wants to join. But yeah, otherwise we could just do the two of us. Yeah, this is a hard one. I think. So yeah, I is the orthocenter of BHC. So oh, but that's not the circumcenter. But yeah, so basically okay, so if K is the circumcenter, we know OK and J are collinear. I wonder. Let AI intersect O at X. Then AIO is similar to IGX. Okay. How did you find that? How did you figure that out? Oh, because sorry, I can't hear you that well on your microphone. Yeah, see if you can turn up your microphone. Otherwise, yeah, you can post it in the chat. I wonder if these are always concurrent. Okay, not necessarily. Okay, draw AW perpendicular to BC. Then angle GIX equals HAIAO. Okay, GIX is WAI is IAO. Oh, that makes sense. So that gives you one of the angles, and then angle, yeah, okay. So that's one of the angles. It looks like IKXG is like an isosceles trapezoid, right? Oh, I think that might be just obvious. Okay. AI over AO is IG over IX. Okay. So AO is the radius. So yeah, how do you get IX? It looks like, yeah, IKXG is an isosceles trapezoid. Let me see if there's another circle that these pass through. I wonder if the circle TSD is tangent to BC. I don't think it is. AI over AO is, yeah, 2IF over BX. Oh, because you used IX equals BX. That's smart. Yeah, in the center X center lemma. Nice. Okay, so that circle's not tangent like I thought it was. Okay, so those triangles are similar. Interesting. So AIO and IGX. All right. So yeah, I like that you use that XI is equal to XB. So AIO. Are SD and X collinear? Yes, that's actually a well-known fact about the Sharkey bevel configuration. So I'm glad you brought that up. They are collinear. And I think they might pass through this point right here. I think they do, and I think I actually proved that in a video of mine. I just forgot about it because I haven't done this stuff so long. But yeah, no, that's a good. SD and X are definitely collinear, and IL should be parallel to BC. So yeah, that might make this a little easier because then, yeah. Let's see. I wonder if there's another point that circle passes through, like a special point. Invert at D with radius root dB times DC. I don't know if I've ever seen an inversion like that before. dB times DC. So yeah, so H goes to G and S goes to X. It's an interesting idea. Yeah, because both the circles have the same power. What D has the same power. It's kind of interesting. So H, so S goes to X. Yeah, let's see where T and H go. Maybe it's something special. So I'm trying to think how I would draw. So yeah, let me do it like this. So I'm going to try that inversion. So we want yeah, let me use the compass. So yeah, really this is the radius we want. Yeah, I don't even need the compass. I could just use, do this. That circle, that's the circle we want to invert about. So let's try it. Let's see where T and H go. So H would go to G. I would go to H. Is that obvious? Yeah. Wait, let's see where T would go. So if I reflect T about the circle. Okay. Yeah, I'm not sure where T goes. S. Where would the whole circle go? Does SH pass through that point? No. Yeah, I just don't know where S and T goes under that inversion. That's the thing. Let me see if there's an easier problem. This one looks hard again. I want to do one easy problem. That one looks tricky. This one looks easy. Let's do this one.